In this video, we present a hypothetical model of how an insect population might change with time that demonstrates chaotic behavior. The idea is insects hatch in the spring, they live through the summer, they die in the fall after they lay their eggs. The number of insects alive during a given summer is dependent on how many were alive the previous summer. So we use the notation N1, number of insects in the first year, N2 for number of insects in the second year, and so forth. Since the number of insects in a given year determines those in the next year, the formula can relate them in a simple model that actually can represent something close to reality is that number in year I plus 1 is related to number in year I times a birth rate number, some constant, minus some overcrowding factor times Ni squared. And so there's a negative sign here indicating the overcrowding factor will decrease the population the subsequent year. And so the idea is that if we choose the units correctly here for the insect numbers, because this is squared, we can actually simplify this to make the parameter A and B the same value. In this case, to do that, the units are normalized such that insect population between 0 and 1. So the question is, if we solve this equation, how does the insect population change with time? How does it depend on the numbers in the first year? And how does it depend on this factor A? So this is a particularly easy type calculation to do in a spreadsheet. And so what we've done is create a spreadsheet with the year and then Ni. We'll start off, for example, N1 value is 0.2. And then N2, say the parameter A is 3.0. Then the formula here is that the next value is equal to A, 3.0, times 0.2 minus 0.2 squared. And then the value we get here will be substituted in to calculate the next value, 3, where again it's a factor of A, and the new value minus the new value squared. Very easy to implement in the spreadsheet. What we're going to show here is just the behavior. So here's where N1 is 0.2, and A is 4, and this is an example of chaotic behavior from a very simple equation. You notice that these variations are not repeating themselves. There's not a pattern developing here. Population goes almost up to 1, almost down to 0, and a given year it varies dramatically. If we change the parameter slightly to 3.4, we get a very stable oscillation. Change to 3.57, we get again this chaotic behavior where it doesn't repeat. We change to 3.0. Notice now it's narrowing around, much smaller oscillations and almost no oscillations for 2.9. And so the point is that with small changes in this parameter, we get big changes. And with a very simple equation, we can generate very nonlinear chaotic behavior in a simple kinetic model.